Hi, my name is Priyanka Jadhav. I'm in the Monday lab section from 3:30 to 5:50 p.m. My crystals were placed at about 9 p.m. on Monday, and as you can see, there's been no growth so far. So the first step that we took was dissolving around 1 gram of aluminum foil and potassium hydroxide to remove impurities, which was an oxidation reduction reaction. The aluminum is oxidized to the +3 state, and the hydrogen is reduced from +1 to 0 in hydrogen gas. The full reaction is 2Al solid plus 2KOH aqueous plus 6H2O liquid yields 2KAlOH4 aqueous plus 3H2O gas, as indicated by the reaction number 1 above. After filtration to remove excess impurities with the Buchner technique, the alkaline solution of aluminum hydroxide is clear and colorless. Sulfuric acid is added, which prompts 2 reactions. The first is an acid-base reaction where the H+ ions from the sulfuric acid neutralize the base to create a thick, white gelatinous precipitate of aluminum hydroxide. Aluminum hydroxide aqueous plus H+ aqueous yields aluminum hydroxide 3 solid plus H2O liquid, which is shown by the first part of equation number 2. As more acid is absorbed, the equation becomes 2 aluminum hydroxide 3 solid plus 3 H2O aqueous yields Al2SO4 3 aqueous plus 6 H2O liquid, since the precipitate of aluminum hydroxide dissolves to give aluminum 3+ ions in solution. At this point, the solution has Al3+ ions, K+ ions, and SOF2 ions as well. The beaker then overall was placed in an ice bath to lower the temperature, which is necessary because alum crystals are soluble in water at room temperature. Upon cooling, crystals of hydrated potassium aluminum sulfate are deposited, yielding KAlSO42 times 12H2O. The final equation is Al2SO4 3 aqueous plus K2SO4 aqueous plus 24H2O liquid yields 2KAlSO42 plus 12 times 12H2O. Finally, the alum crystals are removed from the solution by vacuum filtration and washed with a 50% ethanol and 50% water mixture. This removes contamination from the crystals, but doesn't dissolve them and allows the crystals to dry more quickly. A saturated solution was then created with the alum crystals and diluted water, which was then placed into the small tubes, as we can see here. And within the next few weeks, we hopefully will be able to see some crystal growth. To approach growing crystals of sodium chloride table salt, it's actually relatively simple. You would actually need to start by preparing a saturated salt solution, which you can make by boiling hot water until no more salt dissolves. Make sure that the water is as close to the boiling point as possible, and while doing this, it's fine if undissolved salt settles at the bottom. However, you need to make sure that that undissolved salt does not transfer into your crystal growing container. To create a mass of crystals, you simply pour the saturated salt solution into a vial or another clear container and slowly allow it to evaporate. Crystals will begin to grow on the side of the container. If you would like to create a larger cubic crystal, you have to create a seed crystal. To do this, you need to pour a small amount of the saturated salt solution onto either a saucer or a watch glass. While the liquid evaporates, crystals will begin to form. You can then select a single square crystal from the saucer or watch glass. Now, to grow a big crystal from the seed crystal you create, you pour the supersaturated salt solution into a clean container, still ensuring that no undissolved salt gets in. And after allowing the solution to cool, using a string, you hang the seed crystal in the solution from a pencil placed across the container. You have to make a solution which is saturated and cooled so it won't dissolve the seed crystal. As we did in our own lab, we can cover the container with a Kim wipe or some type of coffee filter to keep out the dust. If you would like to create the perfect crystal, it would be best to use uniodized salt in distilled water. A different type of cooled crystal that we can actually make is rock candy, which involves an entirely different set of materials than both the processes of making alum crystals and NaCl crystals, but the approach to making the sugar crystals is very similar to both of these processes. The first step is to create a saturated solution using 1 cup of water and ½ cup of sugar. Stir it well until no more sugar will dissolve. You have to keep adding sugar a ½ cup at a time until no more sugar will dissolve to ensure that the solution is saturated. There will be about 1½ cups of undissolved sugar. To make a supersaturated solution, heat the sugar mixture until it boils, stirring the entire time. Then turn down the heat and keep stirring until all of the sugar dissolves. Turn off the stove as soon as the solution starts to clear and allow the solution to cool and pour it into jars. Place sticks in the jars that already have sugar stuck to them, and you should start to see crystals growing on the sticks after a few days. By the end of 1 week, there will most likely be many crystals. Although the materials used in this process are much different from the ones we used in lab to make our alum crystals, the general chemistry behind these processes is the same, just in a different order. Similar to the step in lab when we used a hot plate to increase the temperature of our solution as well as a stir bar to dissolve all of the aluminum hydroxide, this rock candy process also involves a supersaturated solution when you heat up the sugar mixture to allow all of the undissolved sugar to dissolve. Our final step involved a saturated solution as we added just a bit more than the amount of solid needed to reach saturation to make sure that we were dissolving as much solute as possible, and we filtered out the remaining undissolved solid. The sugar crystal process also involves a saturated solution when you add so much sugar to the water so it cannot dissolve anymore. The sugar on the sticks are called seed molecules, and the crystals are then formed when sugar molecules in the solutions attach themselves to these seed molecules.